chapter 6 on Lagrange's theorem. We'll start that now. Chapter 6, remember we're skipping chapters 7 and 8. They aren't included. Cryptography is mostly covered stuff that you covered last year. It's not part of the unit, you won't test it. And the algebraic coding theory we're not doing, but those of you who do digital communications will recognize some of that, I think. And then, so for the next 3 weeks, it's chapter 6 and 9. And then Jan takes over and to do chapters 10. Okay, so there's not much really in the reading notes, just a very quick introduction to this chapter 6. So just to connect back to something you've done recently in chapter 4 on cyclic groups, you proved a result in 4.10 that every subgroup of a cyclic group is cyclic. The overall group is cyclic if its elements are really just in one big cycle, starting with the identity, then the generator G, G squared, G cubed, G4, G5, G6, etc., up to G to the power n minus 1, where n is the number of elements in the ring. That's a cyclic group. Well, you proved that every subgroup, you can only have cyclic groups, smaller cycles within the large one as subgroups. And moreover, in theorem 4.13, you proved that the order of any element of a cyclic group, order of an element, is the smallest power of it that gets you back to the identity. Or equivalently, it's the order, the size of the cyclic subgroup generated by that element. You proved that that must divide the order of the containing group. And that's the thing that we're going to generalize to give Lagrange's theorem. So Lagrange's theorem says that in any finite group, G, the order of any subgroup of G is always a divisor of the order of G. That's what we're going to be proving in this chapter. And it's not immediately obvious from the group axioms by any means. The group axioms don't talk directly about the size of the group. And this is a striking result about the size of the group. So it's very universal as to every finite group, every subgroup of that. The size of the subgroup must be a divisor of the size of the containing group. The best way to think about it initially is it places a lot of restrictions on the possible subgroups of a group. Okay? Because if you, as long as you know the size of the group of order 100, group of order 50, whatever, as long as you know the size of the group, then this result immediately restricts the possibilities for subgroups of it. Okay? You can only see subgroups, if you're in the group of size 100, you can only see subgroups of size 1, for the subgroup in the identity, size 2, size 4, size 5, size 10, size 20, size 25, size 50, and then size 100, which would be the whole group itself. Okay? You can only see groups, it's only possible to see subgroups of the group of order 100 of those few orders, because they're the only integers that divide them. So it's impossible. Straight away, you know, a group of size 100, it can't have a subgroup of size 30. 5, because 30 does not divide 100. It's important to note it's not guaranteeing the existence of these subgroups. Okay, so we're not claiming that every group of size 100 has a subgroup of size 50, has a subgroup of size 25. But we are claiming it definitely doesn't have a subgroup of size 30, size 15, that do not divide 100. Okay, but we need to develop a little. The proof is. I'll sketch the idea of the proof now briefly with just a simple kind of diagram. But he uses some technical terms called cosets, which are like a translation of a subgroup within the group. And then the that final bit just refers to this idea of the other direction. So if you've got a subgroup G yeah, the question, is there a subgroup of G of order D, where D is a divisor of G? Well, Lagrange's theorem is silent on that. But it's not necessarily true, and there's the most well-known example, the earliest example of a group, which is here is the alternating group A4, which is size 12, and we'll show that it is no, I think we're going to show it has no subgroup of size 6. So even though 6 does divide 12, nevertheless, this group does not have a subgroup of that size. So converse to Lagrange's theorem is not necessarily true. Okay. The submission problems are 6, 11, and 19. 11, we might prove one or two of the cases of it. It's a early 11. And so I think maybe they're shortish, so I think maybe those for next Monday. Keep us on track. Okay. So we're going to start with a picture. It's going to illustrate what we're going to do. Then we'll look at the notes and we'll work through the discussion of the notes. Okay. Chapter 6. So this is a sketch of the proof of Lagrange's theorem. Okay. The idea isn't too complicated. Okay. So here's a finite group. And it's got a load of elements in it, okay? Wipe your hands of that. Motion detectors. So here's a finite group. Just look as a Venn diagram. Here's a subgroup of it. We know what at least one of these dots is called inside H. No, H definitely contains the identity. So yeah, we can name one of those dots at least. But there's probably a few other ones. Yeah. Okay, that picture at the moment doesn't really tell you how or why the number of things inside H divides the total number of things inside G. Okay. But what we're going to do is, in the same way that the subgroup can be viewed as, a subset of G, some of the elements of G. We can translate H to produce a collection subsets these are called cosets of H. Cosets of H and G. They're like translations. They're a metaphorical way to think about them is taking H and sliding it around the group in certain ways, such that cosets partition G. Partition is a technical term, has precise meaning. So it's a collection of subsets. The union, if you take the union of all of them, you get G, right? So every element is in at least one of the cosets. No elements are skipped out. So the union of the cosets, equals G. So the big union, all the cosets, G. The second condition is that the cosets are disjoint. Okay, so two different cosets have no overlap. Okay. That's the two parts of being a partition of a set. Okay, it's like the way you partition a country. India is partitioned into India and Pakistan, so you subdivide the country. You certainly want to take the pre-existing landmass and don't want to leave any bit not in a country. So you want to make the union of the new subsets be the same as the original subset. So you divide a country in two, and you certainly don't want to have the two bits overlapping. Because if the two bits overlap, then you've got a piece of ground that is claimed by both countries, and that disputes. Okay. But unfortunately, there are some border regions, say, between Pakistan and India, that are contested, and in lots of other instances around the world where.
Isn't the identity of every coset then?
No, the identity is over here. Don't be thinking the cosets aren't subgroups.
Oh, that's why.
They're just subsets.
Okay.
Have I written? Was that written right? Yes, subsets.
Yeah.
Not subgroups.
That's just me not.
Yeah. And the way they're produced are sliding them around. So that's a partition of a group. And so I'm saying to prove additionally, every coset has the same number of elements. Same number of elements. Now, one of the cosets is H itself. As I haven't told you yet, it's explicitly coset, but just think of it as some way of sliding H across into another subset of the group. So as long as we know that all cosets have the same number of elements, and because so that is the size of H, every coset contains order H elements. Then, therefore, that's going to imply that the size of G is equal to the number of cosets times the size of H. Okay. So that proves that the size of H divides the size of G. The size of H is an integer multiple of, sorry, the size of G is an integer multiple of the size of H. Okay. The number of cosets is a count of a number of things, so it's certainly an integer.
And what's the size of H?
The number of elements in it. Speaking generally, so just however, these are the things that these are the technical details that we're going to prove. So we're going to define what cosets are, say exactly what we mean. So this word translate is very rough and vague. You take a subgroup and there's a way to slide it around, move it around so that it occupies different positions in the group, gives you a cosets. They partition G, so they have no different cosets have no overlap. And every element is in some coset. Okay? So to count the number of things in G is just the number of things here, plus 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 the number of things here. And additionally, then, we'll also prove that each coset has the same number of elements. So the total number of things in G, as depicted here, is 4 times the number of things in H. So therefore, H divides the number of things in G. So that's just the generic kind of sketch picture of it. Okay. So now we'll work through the book together and add additional detail as we go. Okay, so that's enough kind of motivating explanation. Now we'll just dive straight into technical detail. So what is a coset? Well, they come in 2 sides, left cosets and right cosets. So what we're starting with here is we're discussing a group G with a subgroup H. And so H is a subgroup of G. A left coset of H in G, left coset of H within the group G, made by a representative little g, is this subset. This is the coset, right? It's a subset of G. It's the subset consisting of all the products little g times H, as H ranges over the elements of H. Okay? So this is one of the left cosets. It's the left coset represented by little g. All the elements in it are G times something from H. That's the left coset of subgroup H in the group G, represented by the element little g. Equally well, you might speak of a right coset. And it's exactly the same construction, except the products are taken the other way around. There you're talking about all the elements little h times g. Okay, so little g is some fixed element, and the options for little h are all of the elements of h. Left cosets and right cosets. Okay, let's immediately look at a concrete example. Let's look at the group Z6, the group of integers modulo 6 under addition. This is the group Z6 under addition. So it's elements 0 to 5, and we're addition modulo 6. So the subgroup we're going to look at is consisting of the elements 0 and 3. So H is equal to 0 and 3. Okay, that's a subgroup. 3 plus 3 is 0. 0 is the identity. So these are the left cosets. So when you add 0 to everything in H, of course, here the operation is addition. So conventionally we'll write it like this: 0 plus H, rather than the identity multiplied by H. In Z6 we're using additive notation. So these are the left cosets: 0 plus H, 1 plus H, 2 plus H, 3 plus H, 4 plus H, 5 plus H. Potentially maybe 6 things. Some of them coincide. Yeah. So the left coset represented by 0 is the same as the left coset represented by 3. The left coset represented by 1 happens to be the same as the left coset represented by 4.
Why?
Well, because what's the 1 plus H? Just if you work it out. 1 plus H, by definition, is the set consisting of 1 plus 0 and 1 plus 3. Agreed?
Yeah.
And that's the set 1, 4. But 4 plus H is the set consisting of 4 plus 0 and 4 plus 3, which is the set consisting of 4 and, well, you're tempted to think 7, but this is within Z6. 7. 4 plus 3 is 1. 1 modulo 6. So it's the same set. The elements come at you in a different order, but as a set, it's the same. And similarly with 2H, 2 plus H and 5 plus H. So there's 3 left cosets. 3 left cosets. Now, of course, in Z6, the operation is commutative. So the right cosets are exactly the same. So 1 plus H is always the same as H plus 1, etc. I hope you can appreciate that that's going to be the same in every commutative group. Okay? So if, in general, if G is abelian, if the operation is commutative, then little g times H, which is the set of all products little g times little h, as H ranges over the possibilities of subgroup H. Well, because the operation is commutative, each element GH is equal to H times G. So what you're looking at is exactly the right coset represented by G. Okay. Because each little product like this is the same as the product the other way around. So the left coset is going to be the same as the right coset. That kind of makes sense when the containing group is abelian. Perhaps if the containing group is not abelian, perhaps we might expect these two to be different. Doesn't guarantee they'll be different, but when the group isn't abelian, these products do not necessarily equal each other. So there's the potential for the left coset to be different to the right. That might happen. So let's look at a non-abelian example, which is the next one, example 6.2. Everybody got that? So in example 6.2, we look at the containing group. So we immediately choose a different one. So S3, symmetric group on 3 letters, all the permutations of 3 symbols. That's not an abelian group. In the first example, we let H be this subgroup here. H is the identity, the cyclic permutation 1, 2, 3, and the square of that. The square of that is 1, 3, 2. Now the size of S3 is 3 factorial, which is 6. The size of H is 3. So by what I showed you in the sketch, we only expect 2 cosets. Yeah, because the 6 elements are going to be partitioned into 2 subsets of size 3. So we only expect two left cosets, and that's exactly what we find. We look at these left cosets. So H is one of the cosets on the left cosets, because get H by the identity times H. Gives you exactly H. And that's the same that you get when you look at any of the elements of H times H. You always get H. If you take one of the elements not in H, then you can get something different. And the 3 choices in this particular example always give rise to the same coset. Okay? So those are the 2 left cosets of H in S3. Now, in this particular example, it turns out that if you look at the right cosets, they turn out to be the same 2 cosets. One of the right cosets is H itself. When you put the identity on the right-hand side, or those other elements on the right-hand side, you get the same coset. And at the top of the next page, you take the other elements and you put those on the right, you still end up with the same coset. But that's not always the case. Because this containing group is non-abelian, we can find examples where the left cosets differ to the right coset. So here's a second example, still based in S3. In the second example, we're dealing with the subgroup K, which is this here. This is an order 2 subgroup. Yeah. S3 still is size 6, so we expect to see 3 cosets. When you look at the left cosets, well, if you multiply K by any element from K, you just get K again. If you look at other elements times K, you get different subsets. Okay? These 2 elements give rise to the same subset, so the cycles 1, 3 and 1, 2, 3. And the other 2 cycles, the 2 remaining cycles, also give rise to the same left coset. So you got those 3 subsets. K, the subset, that subset, those are the 3 left cosets of K in S3. But when you look at the right cosets here, you see something different. Again, K is one of the right cosets. You multiply K, if you look at the coset represented by the identity, the right coset represented by the identity, that's going to be K again, the same subset. But the other 2 right cosets are different to the subsets that arose as left cosets. This is more the typical behavior when you're in a non-abelian. You're in the non-abelian group, the typical subgroup, the expectation is that the left cosets will be different to the right cosets. We'll discover in the exercises that there are certain patterns you can spot, certain conditions you can see that will make the left cosets equal to the right cosets, even though you're in a non-abelian group. But that would be the kind of typical expectation if you're just looking at a non-abelian group, certain subgroup. So this is what we mean by translating the subgroup. How do we translate the subgroup? How do we move it around the group? We simply hit the subgroup with this particular element. You choose an element from the group, say the cycle 1, 3 from S3, and you hit everything in K with 1, 3 on the left. So the 2 elements in K, so you have 1, 3 times 1, 1, 3 times 1, 2. And that gives rise to these 2 elements. And that's the way you take your subgroup K and you shift it somewhere else. You choose another element in the group, multiply the subset on the left or on the right by another element, and that shifts all the elements of the subgroup across into a new subset of the group. So that's this kind of visual or geometric metaphor of translating translating the subgroup across. Okay, any questions about those examples, or if I could clarify? We didn't get down to we didn't spend time working out the individual products of this permutations. You can check all that detail. What we're just observing here is the way that the subgroup gets shifted around in the container. In each case, what we've seen here in these examples is the different cosets, they certainly all have the same number of elements. Yeah, they've all got 2 elements in this example. They're disjoint. Yeah. And all of they don't miss out any element from S3. Every element of S3 can be found in one of the cosets. Yeah. There's only 6 elements in S3, so here they are. Yeah. Okay. So that Venn diagram sketch we can kind of see it happening in at least 2 examples here. Z6 example and in this K example, right? In the S3 example. We saw it for 2 different subgroups of S3. Okay. Now here's lemma 6.3, just building up something about left and right cosets. You often get these results when you introduce new notation and new concepts. This lemma is just saying that all these statements are equivalent. Each one implies all of the other ones. This is one of the exercises you're going to do. This is question 11. But there's just short little arguments for each one. We'll show a couple of the independencies here, and then you can compress. So we're dealing here with a subgroup H of a group G. So let's look at proving 1 or 2 of these. So this is lemma 6.3. So it's saying that they're all equivalent. So let's assume 1. I.e., we're assuming that G1H is equal to G2H. I mean, some of them are. Let's look at deriving 4. Okay. Well, G2 is certainly an element of G2H, since G2 is equal to G2 times the identity. And the identity is in H. I'm trying to prove 4. G2 is an element of G2H, since G2 is equal to G2E, and is an element of H. So that implies that G2 is an element of G1H, because G1H is equal to G2. So we can say G2 is equal to G1 times little h for some particular little h, the subgroup. So that proves 4, henceforth. G2 is in G1H. Can also quickly go on to derive 5 from that. Notice also that G2 is G1H. That implies if you multiply both sides on the left by G1 inverse. G1 inverse times G2 is equal to G1 inverse times G1 times H, and so that's equal to H, which is of course an element of the group capital H. So that's G1 inverse times G2 in inverse times G2 is an element of H. So hence 5. So there's just a little move from one of these statements to any of the other ones. We proved there that 1 implies 4, and it also implies, and that 4 implies 5, so that tells you 1 implies 5. You just prove enough links in between the other statements so that you can, from any one statement, you can go to the other statement. So these are all, the way to think about these, they're all equivalent ways of saying the left coset represented by G1 equals the left coset represented by G2. That's what it literally says in part 1, G1H equals G2H. But if you can, it's the same thing as saying that one element is in the left coset represented by the other one. That's quite a nice one, part 4. G2 is an element of the left coset represented by G1. That's equivalent to the two left cosets being the same. So in our examples before, we've seen multiple instances where different elements give rise to the same left coset. So you can look at these examples and imagine this is your G1 here, 2, 3, and your G2 is 1, 3, 2. And you can verify those other statements as well with reference back to those examples. But just these little 1 or 2 line arguments can be used to prove the linkages between any two of those statements. Is that okay? Okay. So I think now we're ready to start building up to prove the necessary bits and pieces to prove Lagrange's theorem. We've got the concept now of how you take a subgroup and produce new subsets of the group. For the cosets, we're going to focus on left cosets, say. Kind of already seen why the union of all the cosets is G and all the cosets are disjoint, but we'll prove that carefully now. And then additionally, we just have to prove that they all contain the same number of elements. Once we've got these 3 facts, that they partition G and that they different cosets of the same number of elements, that proves Lagrange's theorem. Just by a simple counting argument. Number of things in G, just count up the number of things in each subset. We've all got the same number, so it's some number times the number of things in H. So, theorem 6.4, so it's written about left cosets. So we let H be a subgroup of G, and the claim is that the left cosets of H in G partition G. That is, G is the disjoint union. It means that G is the union of all the left cosets, and different left cosets have no overlap. Are disjoint. So the proof of theorem 6.4 notice that G is an element of G, then G is an element of the left coset represented by itself. Okay? Since G is equal to G times the identity, and the identity is an H. So any element is always in the left coset represented by itself. So that implies that the union of the cosets, union of all the cosets contains G. Yeah, because every element of G can be found in one of the cosets. But we already know, since each coset is by definition a subset of G, how they're defined. They're defined as sets of products within G. Each coset is certainly a subset of G. That implies that the union of cosets, he says it more carefully in the way he writes the proof in the book, but the union of cosets, that means it's contained within G. I should make those contains or equals, I guess. By definition, the union of all the cosets is a subset of G, because each coset is a subset. It's still a subset of the set. But that first argument shows every element from the set can be found in at least one of the cosets. So therefore, the union of all the cosets contains the group, because all the elements in the group are found in the union of all the cosets. So once you've got these two, star and star star, imply that G is equal to the union of the cosets. Agreed? So that's one part of being a partition. The union of the subsets is the whole set. The second part is showing that they don't overlap. Secondly, for cosets G1H, G2H, you need to prove that G1H intersect G2H is equal to the empty set, or we are in fact looking at the same coset. Okay, so this is what we mean by being disjoint. Different cosets have empty intersection. So for any two representatives, a little G1 and a little G2, we have to be able to prove that, well, maybe they're the same coset. In which case, it's just the same coset represented by two different representatives. Or the two cosets have no overlap. So the way we do this, the way we prove this, is to assume that typically the intersection might be empty. So we assume the intersection is not empty. So what we're trying to conclude from this is that the two cosets must be equal. If the intersection is not empty, that means there exists an element, what's he call it? He calls it A. There exists an element A, such that A is an element of G1H and A is an element of G2H. Okay, so there's something in the intersection. So if the intersection isn't empty, pick one of the elements from the intersection. So that implies that there exists a H1 and H2, two elements of H, such that our A is equal to G1, H1. Still A is also equal to G2, H2. Now we have to allow H1 and H2 to be potentially different elements. Okay. We're not saying, when you say that something is in the left coset and the right coset, we're not saying it's the same element of H that gives rise to A in both cases. Just that you can write A as a product of G1 times something from H, and you can write A as G2 times something from H. But then what we can say is if we multiply both sides, say by H2 inverse, G1, H1, H2 inverse is equal to G2. You multiply both sides on the right by H2 inverse. Forget about A for a moment. Well, that implies that G2 is an element of the coset G1H. G2 is an element of the coset G1H. So by the previous lemma, which you're going to complete in the exercises, by lemma 6.3, G1H is equal to G2H. So if the intersection between left cosets is empty, the two left cosets must, sorry, isn't empty, two left cosets must be the same. So if they've any overlap at all, they're in fact the same. You don't have different cosets, they have a little bit of an overlap. Don't have either completely separate or they're the same thing. So they're disjoint. So this shows, therefore, cosets, the left cosets, partition G. Left cosets of H and G, partition G. The same theorem is true for right cosets. Drive the right-hand side, just change the approach of things. Do good things on the other side. Do the multiplications on the other side. Okay, but it's the same situation. The right cosets of H and G. Terminology that's introduced. Terminology, notation that's been slipped in here. This notation denotes the number of left cosets number of left cosets. It'll turn out to be the same for the right cosets. The number of left cosets of H and G. Called, the index. Slightly shorten the number of words you have to use. The index of H and G. So if you speak of the index of a subgroup within its containing group, it's the number of left cosets of the subgroup that there are. Now this can still make sense even if Hg is infinite. In the definition of coset, in the results we've proved so far about cosets, we haven't actually used the fact that G is finite anywhere. So what we've said goes equally well for infinite sets. And it may be, if G is infinite, well, its subgroup could be finite or infinite. If you have infinite G, a finite subgroup H, then the number of left cosets would have to be infinite. To split an infinite set into subsets of finite size, you'd have to have an infinite number. But if you had an infinite group and the index of an infinite subgroup in it, then that could be finite. Not strictly speaking, it's not necessarily finite, but you could have a finite number of left cosets of an infinite subgroup within an infinite group. Okay. So the index of H and G is simply the number of left cosets of H and G. Now, how are we doing? So I'm going to skip theorem 6.8. Theorem 6.8 proves that the number of left cosets is the same as the number of right cosets. Always. The number of left cosets of H and G is the same as the number of right cosets of H and G. That means there's an unambiguous index of H and G. You don't have to say the index of left cosets or the index by right cosets. It's in fact the same. The number of cosets. The individual left cosets might be different to the individual right cosets. It's the same number of them. That's the point. So I'm skipping it just so in the 3 minutes we can complete the proof. of Lagrange's theorem. Because the only piece missing is proposition 6.9, which says that all the cosets have the same number of elements. And the way we prove that is that the number of elements in the subgroup H is the same as the number of elements in a left coset, represented by the element. And as is typical in kind of set theoretic arguments, how do you prove that two sets of the same size? The way you prove the two sets of the same size is you set up a bijection between them, one-to-one and onto mapping between them. Because any time you count the number of objects, if I count my number of pens, 1, 2, 3, 4, what you're doing is setting up a bijection from the numbers 1, 2, 3, 4 to the individual pens. Naming each of them. That's pen number 1, that's pen number 2, pen number 3. Setting up a bijection between the two sets. So that's what we do. If we want to show that every left coset has the same number of elements, well, we take the coset H, the subgroup itself, as our original coset, and we show that there's a bijection from that to every other left coset. And the bijection is going to be a mapping phi from H to the left coset GH, and there's only really one way to define it. What's the value of phi of an element little h? It has to be G times little h. What else could it be? How else do you take an element little h from H and associate to it a meaningful element in the left coset? There was really only one choice, G times H. That's certain. G times H is certainly an element of the coset, and it's the most natural one to associate to little h. The most natural, obvious in a way, map. So the proposition, the thing you have to prove is prove the bijection. So suppose, so yes, shows 1-to-1 and onto. So first we show that it's 1-to-1. So we assume that phi of H1 is equal to phi of H2. And that would be a problem if H1 and H2 are different, because that shows that it's not 1-to-1. We've got to prove that H1 is equal to H2. H2 is G times H2. So we're effectively assuming GH1 equals GH2. The same element G on both sides, so you just cancel G. You multiply both sides by G inverse on the left. And that tells you that H1 is equal to H2. So the only way to see the same value come out of the phi function, that phi of H1 is equal to phi of H2, that's it, give it the same argument. That means it's 1-to-1. Yeah. You give it different arguments, it gives you different values. That's injectivity, showing it's 1-to-1. Next, we must show that it's onto. Well, it's, by definition, it's onto. The codomain is the left coset. That consists of all elements that form G times little h. Well, h is equal to G times little h. So by construction, you see it's naturally onto. Just by definition of what it is, it's onto. So it's 1-to-1 and onto. Therefore, the two sets, the domain and the codomain, have the same number of elements. Okay. Bring everything back to H. So every left coset, the number of elements that it has is the same as the number of elements of H. We've proved in the previous proposition that the cosets partition. True? So all he's got written down here in the proof of this here, all he's got written down is just a sentence articulating this fact. You know the cosets partition G? Well, you can count the things in G by counting them up coset by coset. But you're going to find the same number of elements in each coset. For R is just the number of cosets times the size of H. It almost seems, it almost seems like the proof is too easy in some ways. I know I hate saying things like that because when you see anything for the first time, it's not easy. But it's very surprising to fit into one class. Well, we proved the theorem about every single finite group there is in the universe. in the world. Every finite group, subgroup of that group, the size of the subgroup has to divide the size of the exchange group. And it falls out relatively easily from the definition of a basic fact. Okay. So tomorrow we'll review that slightly, and we'll look at some associated problems and some nice consequences, some nice applications of it. Okay. So thanks for your attention. I shall see you tomorrow afternoon.